In the autumn of 1839, a violent storm hit the Thames Valley and tore out the timber scaffolding beneath a newly built railway bridge at Maidenhead. The wooden centering that had been sitting under both arches since construction was destroyed overnight, swept away by floodwater before anyone had formally decided to remove it. The engineers who arrived the following morning expected to find collapsed brickwork. What they found was a bridge that had been standing unsupported for months without anyone knowing it. The scaffolding had not been holding anything up. It never had been. The arches had been carrying themselves from the moment the mortar cured. The subscribe button you see below this video means a great deal for the future. A structure built beyond all reasonable requirements will outlast any era that questions it. The Maidenhead Railway Bridge was described as reckless by the best engineers of its time, but it still stands safely, carrying trains. That's why you should like the video and subscribe to the channel. The Maidenhead Railway Bridge cost £37,000 to build and opened on 1 July 1839. It has carried every train crossing the River Thames on the Great Western Main Line ever since, for 6 years, through 2 world wars, through the introduction of locomotives that weighed 10 times what the original engines weighed, through electrification and the introduction of 125-mile-per-hour services. It remains, to this day, the longest and flattest brick arch bridge ever built anywhere in the world. Not the longest in England, in the world. A room full of England's most respected engineers said it would certainly fall. They were wrong.
Almost
in
there.
1833, Isambard Kingdom Brunel was appointed chief engineer of the Great Western Railway at the age of 26. The brief was to build a railway from London to Bristol, 118 miles, as direct as possible. Brunel attached a condition of his own. The line would have no gradient steeper than 1 in 1320 feet, 1 foot of elevation change for every 1,020 feet of horizontal distance. By comparison, the railways being built around him at the same time climbed at 1 in 75 or steeper. Brunel refused all of it. A level railway would run faster, burn less fuel, and wear its locomotives and track less severely over decades. He was not designing for 1835. He was designing for whatever came after. Every hill in his path, he cut through. Every valley, he crossed at track level. This produced the Sonning Cutting in Berkshire, 2 miles long, 60 feet deep, dug by hand by 3,000 navvies. It produced Box Tunnel near Bath, 2 miles bored through solid limestone at enormous cost and human toll. And when the route reached the Thames at Maidenhead, it produced a problem that forced Brunel to do something no brick engineer had attempted before. The Thames at Maidenhead is 270 feet wide at the crossing point, with low chalk banks and a central navigation channel used daily by barge traffic. The Thames Navigation Commissioners had standing rules. Nothing could obstruct the navigation or the towpaths on either bank. No pier in the water. Sufficient clearance beneath. These constraints meant a single long span over the navigation channel and another over the towpath. 2 arches each of substantial width, with almost no vertical space to work with if the 1 in 1320 gradient was to be maintained through the crossing. Most engineers given this brief would have raised the arch profile. A steeper curve was safe, precedented, and straightforward to calculate. But a higher arch meant a hump in the track, and Brunel would not move on the gradient. So instead he designed 2 brick arches, each spanning 128 feet and rising only 24 feet, a span-to-rise ratio of 5.3 to 1. No brick arch of this flatness had ever been built at this span. No one had proved it was possible. Several of the most senior engineers in England stated publicly that such arches would be incapable of supporting their own weight, let alone the weight of a loaded train. When Brunel presented the design to the Great Western Railway Board in 1836, the reception was poor. The field of structural analysis was still developing, and most practitioners worked from empirical rules derived from semicircular arch geometry. Brunel's design fell entirely outside those rules. He had applied then experimental calculus-based modeling to calculate the line of thrust through his arch geometry, showing mathematically that the forces would remain stable within the arch ring under every load condition he could model. The board was not persuaded. Several directors demanded the design be revised. Brunel held firm. Construction began in 1837 under resident engineer John Wallace Hammond and contractor William Chadwick. The arches were built ring by ring from curved timber centering, wooden formwork that supported each course while the hydraulic lime mortar cured. The bricks were London stock, a pale yellow material fired from Thames Valley clay. Course by course, over many months, the flat elliptical shape Brunel had calculated rose above the river. In 1838, the centering beneath the eastern arch was partially eased, the standard procedure to test whether the arch could begin carrying its own load. 3 of the lowest brick rings settled and separated from the body of the arch over a section approximately 30 feet wide. The critics had their proof. The arch was failing. Brunel inspected the damage and identified the cause. Chadwick had eased the centering before the mortar had fully cured. The arch had been asked to carry load before it was ready. The geometry was not wrong. The timing was wrong. Chadwick accepted responsibility. Repairs were made. The centering was reinstated. In October 1838, it was carefully eased again with Brunel present. Nothing moved. The GWR board, still not convinced, ordered the timber centering to remain in place indefinitely as visible reassurance. Brunel agreed. Then, quietly, he had the frames lowered a fraction of an inch so they no longer contacted the arch soffits. They sat beneath the arches, appearing to support them, touching nothing, doing nothing. The directors believed otherwise. Then came the storm of autumn 1839. Floodwater rose and the wind destroyed the centering before anyone had arranged to remove it. Engineers arrived the following morning, expecting ruin. The arches stood perfectly, as they had been standing for months. The critics went quiet. The bridge opened to traffic on Duidelijke Witten Verrij. The cry did Zimpuls. The July Duidelijke Witten Verrij. The cry did Zimpuls of Botring gedoort straal, kom brals, lathiken doort redhounes de faal wischen faun. What those arches relied on was geometry, not mass. In a conventional semicircular arch, the line of thrust, the path along which compressive forces travel through the structure, follows the arch curve naturally. The form and the forces coincide. In a flat arch like Brunel's, they do not coincide naturally. The thrust line must be kept within the arch ring by precise calculation. With a span of 128 feet and a rise of only 24 feet, the arch ring is narrow relative to its width. Any error in the geometry, a deviation in the brick placement, a variation in mortar stiffness, and the thrust path exits the ring. The arch fails in seconds. The only thing preventing failure is accuracy. Brunel's accuracy was sufficient. The arch he calculated in 1836 was so precisely formed that no engineer in the 6 years since has found reason to fundamentally alter it. When the bridge was widened in the 1890s to carry 4 standard gauge tracks instead of 2 broad gauge tracks, the civil engineer Sir John Fowler replicated Brunel's arch geometry exactly on both sides of the original structure. Not because the contract required it, because nothing better existed. The original London stock brick arches are still there, embedded inside the later widenings, carrying a share of every train that passes. The boundary between Brunel's 1838 brickwork and Fowler's 1890s extension is still visible from beneath the bridge, pale brick meeting red. 2 construction campaigns, 60 years apart, joined without modification because the older work was already precisely right. By the early 20th century, locomotive weights had grown well beyond what any Victorian engineer had modelled. The bridge was examined. The arches were operating comfortably within their safe load limits. No intervention required. In the 1950s, heavier locomotives, faster schedules, increased frequency. Examined again, same conclusion. In 2012, the entire structure was upgraded to Grade 1 listed status, the highest designation available for historic structures in England. The Historic England assessment confirmed that the 2 main arch spans remain the longest and flattest brick arches ever constructed anywhere in the world. Today, the trains are electric, running at high speed on the Elizabeth Line and the Great Western Main Line. Walk along the Thames path, and you pass directly beneath the right-hand arch, the sounding arch, named for the acoustic echo it produces. Look up, and the brickwork from 1837 is above your head. The mortar joints are intact. No cracks, no spalling, no sign of distress after 6 years of continuous heavy loading. Somewhere above you, a train crosses. The vibration is barely perceptible. This is what 6 years of correct engineering feels like from the inside. Not impressive, not dramatic, permanent. Today the trains are electric, running at high speed on the Elizabeth Line and the Great Western Main Line. Walk along the Thames path and you pass directly beneath the right-hand arch, the sounding arch, named for the acoustic echo it produces. Look up and the brickwork from 1837 is above your head. The mortar joints are intact. No cracks, no spalling, no sign of distress after 6 years of continuous heavy loading. Somewhere above you, a train crosses. The vibration is barely perceptible. This is what 6 years of correct engineering feels like from the inside. Not impressive, not dramatic, permanent. One writer summed up the bridge's history in the late 19th century. Some 60 years after completion, the contractor had begged Brunel to let him abandon the contract, certain the arches would collapse. Brunel proved to him mathematically that they would stand. The contractor went through the entire construction period in fear. A storm destroyed the centering before it was due to be removed. The bridge stood. It has stood ever since, quite safely. What Brunel built at Maidenhead was a proof that precision applied without compromise produces outcomes that outlast every era that doubts them. The budget pressures, the critics, the shifting fashions of structural practice, none of it matters if the original calculation was correct. Today, a project of this kind would face years of value engineering review. Safety margins would be trimmed until the numbers just passed the required minimum. The structure would be designed to last 50 years and then reassessed. Brunel designed for indefinite service on an experimental main line at a cost of £37,000, and the result is still standing and still correct after 186 years. In 1839, a crowd stood on the Thames riverbanks to watch the first train cross. Some of them had been certain the bridge would fall. They were wrong. The bridge did not register their doubt. It carried the train and waited for the next one. Here again you see a mega structure born from the intelligence of a talented engineer. If you would like more videos like this, please like the video and subscribe to the channel.